All right. So, welcome back to class. Algebra 1, Abstract Algebra 1 students. All three of you, yes. Okay. And one of them is Guru, who's not a student. Interesting. Interesting attendance. All right. So what I need to do today, though I'm not sure I should start yet, because there's only three. Well, actually, in Discord, there are the three people online, and two are offline. So I'm assuming that 3 out of 5 people are attending. Refresh this. Change? No. Okay. Well, I have 45-minute lectures, so I can't waste time. And students should show up on time. Okay. All right. So what we're gonna do today is an exciting day, very important day. If you haven't taken abstract algebra before, in fact, let me start a poll for my students who can't possibly all be in. Oh, now maybe they're here. Okay. Let me start a new poll. Students, have you seen the definition of a group before? Let me say yes and no. All right, you have 1 minute. Look on top of your chat, and go ahead and. I just want to see. Yep. Okay, 3 of you have. 1 no. Okay, good. That's enough information. That means I have to cover it carefully. Okay, good. So here we go. Thank you. So here we go. Definition. All right. So the definition looks dry. It always looks dry in every abstract algebra course. It always looks very dry. So once I put the definition up, we have to do something that's absolutely mandatory in all higher mathematics. And that is that every time you see a weird dry definition, you should go and try to find as many examples and non-examples so that you understand what the definition is trying to isolate, what concept. The concept is only going to be apparent to you to the extent that you have a huge bag of examples and non-examples, because that's kind of what a definition carves out. It carves out a bunch of objects and situations that are in the definition, and therefore it also cuts out all the stuff that's not captured in the definition. So the more territory via examples that you can sort of cover, the more you understand a definition. Okay, so the definition goes like this, and it's kind of, every mathematician is trained early on with this definition. So let's see if I can actually pull it out of my brain. Okay, the definition of a group. A group. So a group is, first of all, a set. Okay. For us in most undergraduate All undergraduate classes, everything's a set starting off. So that's nothing yet. A group is a set which has been equipped with a binary operation which I'm going to write as little dot, like multiplication dot, like A dot B. Okay? Equipped with a binary operation, A dot B. What that means is for every pair of elements in the set, G, A and B, A dot B is also an element in that set G. Okay? Just there's a notion of combining two elements to get a third. And we call that, we're just going to give a symbol dot for that. Or juxtaposition, AB. Or A star B. Some notation for this binary operation that is part of the definition of a group. Okay? It's equipped with a binary operation satisfying, the operation satisfying. Okay. So 1, associativity. That is A dot B multiplied with C. Okay, we just freely use the words multiply, dot, I don't know, maybe only I use it, mostly multiply, but it's not, okay, this is a word, A dot, just put dot. A dot B dot C always yields the same result as A, but then doing this. This is an order of operations. The order in which you do parentheses does not matter. That's a property that's enforced on this binary operation. We're requiring that. We require that of the operation. Not all operations that you can just create, just random ways of assigning a third element to a pair of elements. Not that most of them won't satisfy associativity. So it's a strong requirement. 2, identity. There exists. So by the way, in number 1, this is for every 3 elements in the group. All right. There exists an element E. It's traditionally denoted E, okay, for identity. Probably because of that. So there exists an element E in a group, such that E times G equals G times E equals G for any element in the group. I'm just going to use all kinds of letters for elements in the group so you don't get too attached to just one symbolic system. All right? So it's an element such that when you multiply dot with it, you recover yourself. But also notice how we're careful to put the dot in both directions. So more on that soon. 3, inverses. For every element in the group, there is another element. Or itself. I mean, there is some element in the group such that when you multiply both ways, oh, I guess I'm using little dot to denote my multiplication, you get the identity element that was specified in part, whose existence was referred to in part 2. So it's important to write part 2 the second condition before you write the third, because the third one refers to this magical element that is declared, that is required when you're facing a group. All right, so a group is this. All right, it's a thing, it's a collection of things where there is a notion of combining two things to form another thing, where that combining notion, that multiplication notion, that pairing notion is associative. So the way you resolve parentheses and the order by which you do the resolution of parentheses doesn't matter. There is a identity element that multiplies, and multiplication has no effect. And then there's always, for every element, there's a inverse element, kind of a reciprocal, which when you compose an element with that inverse, you get back to the neutral identity element, which was declared to exist in part 2. All right, so now the first thing we do is just drown ourselves with examples. So that's what we have to do next in our 45-minute lecture. So drown ourselves in examples. All right. And in a sense, if a student does not go and investigate examples and play around in them, they will have a bad time. They will eventually not feel comfortable in group theory. So this is absolutely essential. Okay, so here's an example. Here's a classic example. Okay, actually, I'm going to do one of the most disgustingly stupid examples. Okay, stupid example. Extremely stupid example. Stupidest example. Okay, so here's my group. To specify a group, you need to tell me a set, and then you have to specify the multiplication law, the binary operation. Okay. No. Closure is part of the definition of what a binary operation is. It's in the what a binary operation means is when it takes two elements in the group, it spits out another element in G again. So it's implicit in there that we have closure. Okay, the stupidest example. The group G will be the following set of numbers. It's a set that has one element, and it's the number 1, like number from kindergarten. 1. It's one element, and the multiplication law, the group law, that's a word. Oh, vocabulary. Group law, group multiplication, the binary operation, the group operation, the composition rule, the combining thing. No one uses that, but group law. Let's use group law. Is ordinary multiplication of numbers. Multiplication of numbers. From kindergarten. Okay. Here's something to remember. A good thing to remember. Multiplication of numbers has been associative this whole time. So multiplying numbers has always been associative. So it's like that's known. Okay, has always been associative. All right, so you don't have to check associativity when we're multiplying a bunch of numbers, if that's the context. If the group law is inherited from just multiplying numbers. Okay, so it's associative. You could also just check that it's associative because there's only one element to talk about. Okay, so associative, good. Identity. identity element. An identity element. Notice I have to use the word an instead of the identity. We don't know that identity element is unique, nor do we know that inverses are unique for every element in G. There's a unique H. We will prove those small little tiny theorems on Monday for sure. Okay? So for today's class, I'm going to have to use the weird phrase an identity element. Okay, but secretly, it's going to be the identity element. Identity element. 1. 1 times 1 is 1. And then 1 times 1 the other way is also 1. So there you go. I just checked it. It's the stupidest example ever. And then inverses. Inverse. 1 is an inverse for 1. You have to go through the whole group. You have to go through the whole group and ask, does every element have something else that when you multiply with it both ways you get the identity element? 1 for us. Yeah, 1 is its own inverse. 1 times 1 is 1, and then also 1 times 1 is 1. The most stupid example of a group. But it's technically the first example. Because you gotta have some elements. You can't have an empty set, because you have to have an identity element. So this is, in some sense, the smallest group imaginable. It's called the trivial group. All right? Stupidest example. There you go. All right. Got that crap out of the way. Next. Okay, next example. So a little bit better. A little bit better. Just barely, though. Just barely. Okay. Here's a set. G is the set of 1 and minus 1. Just the two numbers. And the group law is multiplication, like of numbers, of integers. Notice that the group law takes pairs of elements in this set and outputs still an element in this set. Like 1 times minus 1 is still in here. There's closure in this group law. This group law is truly a binary operation on this set. Okay, good. So this thing is associative because multiplication is associative. An identity element is 1. 1 times anything is itself. And inverse. 1 is its own inverse. And minus 1 is also its own inverse. So each of these elements has some inverse element. So everybody's got an inverse. Great. All right, so this is a group. This group has 2 elements. This group has 2 elements. All right? Here's some other ways that we'll write this. This sentence, this group has 2 elements. Here's some other fancy way to write it. The magnitude of the group is 2. That's another way of saying this. I'm just introducing notation slowly. The group has order 2. The order of this group is 2. Just words. Different ways of saying how many elements the group has. This is a group that has 1 element. Its order is 1. It has that many elements. Okay? Okay. Little bit juicier still. A little bit better. The integers. G is now the integers. Z is how we denote the set of all integers, positive and negative. This stuff from maybe first grade, because you didn't know what a negative number was in kindergarten. Okay. That thing, integers. And the group law, the multiplication law, the composition law, the group law is let me just say it like this. The group multiplication operation is addition. The group multiplication is addition. All right? The word multiply in the setting of group theory is not meant to freeze one example of one setting. It is just some notational choice that we made just to talk about the concept of the operation that is combining two elements to form a third. Addition is such an operation. Hi, Shirshak. How are you doing? Okay. Yes, I need to focus while doing this. Okay. Next. So addition, why? You have to check. So addition has always been associative, like from the beginning of ancient Babylon. Okay, so adding numbers, just like multiplying, has always been associative. We'll just take that as like a property of numbers and adding. Like 2 plus 4 plus 9 is always 2 plus 4 plus 9. Like those two things will give you the same result. Okay. All right. So associative. Next, the concept. What's the identity? Yeah. So what's the identity element? The identity element is, of course, 0. 0 plus anything is anything plus 0 is the anything. Right? I'm verifying property number 2 for you. Okay, that's true. Inverses. Okay, inverse. The inverse, an inverse, right now it's an. We're going to fix that one day. An inverse of the element 5 is minus 5. Inverse is negation. This forms a group because 5 plus its negative is back to the neutral element 0, is the neutral identity element 0. Okay, so this is an amazing group. It has infinitely many elements. Notice this is a group that has infinitely many elements. Okay, it's a group, an infinite group. This was a finite group. And so was the previous. So here's an infinite group. Oh, fantastic. How else do you say this? It's a group of infinite order. Infinite order. It's a group that has infinite order. Z. The integers under addition. You'll see this kind of language for specifying a group. The integers, that's the set. Under, this word is now gonna, after under, you write what operation you're thinking of on this set. Under addition. Is a group. Integers under addition forms a group. Form, I suppose. A group. Okay. Now, there's something funny about the examples so far. So far, just a note. So far, the operation, the group laws / operations in all our examples so far have all been commutative. Because look, multiplying two numbers doesn't matter what order you multiply them in. But notice that in the definition, there was no mention that A times B is supposed to be B times A. No, we don't want to put that because we're trying to extract out one grand common denominator that's common to many, many different situations in mathematics. Notice that we've got here multiplication with 1 and -1 as the elements, and then, also integers and the addition operation are under this massive umbrella. Many, many situations. We're trying to capture many situations, abstract out one common denominator, and just do the algebra or say what's true about this very general situation so that we don't have to reinvent the wheel every time we see another group that shows up in mathematics. Okay, but notice our examples so far are commutative. Adding, doesn't matter which way you do 5 plus 7, you get 12. So next example we should do is non-commutative example. And this is a classic. Okay, the example is this. The group G is going to be the set of 2 by 2 invertible matrices. With, let's just put what kind of numbers are in there, with real number entries. Let me write some examples for you, like 2, 7, pi, 4. This is an element in G. How do I know that? How do I know it's invertible? Let me recall for you one of the coolest things in your elementary linear algebra class. This is in G because the determinant is non-zero. So let me remind you what the determinant is. It's the determinant of this matrix is A times D minus B times C. And if you do that for this, you get 8 minus 7 pi. And that's not, that's non-zero. Its determinant is non-zero. Did I say 0 earlier? Non-zero is not the number 0. Okay? And that tells you that there is an inverse for this matrix. And I'll write the inverse here in a second to remind you of this handy formula. Okay, so the set is invertible 2 by 2 matrices. Okay, and the operation, the group law, is matrix multiplication. So you have like A, B, C, D times A prime, B prime, C prime, D prime is, oh my God, it's like this. It's like, I don't know, A prime plus B, C prime. And then C, A prime plus D, C prime. It looks way fancier when you write it all out like this, but you know what it is. B, D prime or something. And then C, B prime plus D, D prime. That is the binary operation, matrix multiplication. Fascinating. Okay, so linear algebra is, at the end of the day, group theory. Okay, so it's not a joke, this whole group theory thing. It is a massive, think of it as a massive umbrella concept that many of your math education situations or operations were instances of. This is a huge deal, extracting out the definition of a group. It's kind of like someone revealing finally that, like, look, a lot of the things you did in math classes, they were only superficially different looking. Yeah, there are some new things that happen in certain contexts that are not happening in others, but there are some common denominator things that were always present, and we're going to learn all the common denominator things whenever we have this setup. A set with a binary operation that has inverses, identity, and it's associative. So associativity, it's a pain in the ass, but literally you can show left-hand side equals right-hand side just by following the definition of matrix multiplication. But you can do, you have to write 3 matrices now, like, and then multiply the first pair, and then extract the result, then multiply the third, versus multiply the second pair, and then the first one on the left, and check algebra, both sides are equal. So do left-hand side equals right-hand side, and algebra. Okay, it's algebra because look at this, it's algebra. This is algebra, like look, plus, times, symbols, doing algebra. Okay, so pain in the ass, but you can do it. All right. Okay, second, hi Slayer, how's it going? So I give 45-minute lecture, so I have to go sort of fast. All right, I have to concentrate. Okay, associativity. Identity. Identity. Here we go. Yeah, there is an identity element. There's this one element called, in linear algebra, they called this element the identity matrix for some reason. All right. And then there's inverses. If you have an invertible matrix, the definition itself says that that means that there's some other matrix that when you multiply, you get the identity, right? But let me show you what that matrix is. Okay, so if you have this matrix, and you know it's invertible, here's what you write down. You write down 1 over the AD minus BC determinant. This is a formula for the inverse of a 2x2 matrix. You should probably remember this. AD minus BC. No. Sorry. I already extracted out that. I brought that out of the whole matrix. So you just swap the diagonal entries and you negate the off diagonal. If you go and do your matrix multiplication here of these two elements, a G, and then we're saying H is this thing. If you do that, you'll get back your identity element. And you're only going to be able to do this if your determinant is something that's not 0, so that you can actually write that 1 over number down. Okay? So this matrix, the 2x2 matrices that are invertible, we're just putting that condition, invertibility, in so that we get inverses. And the operation being matrix multiplication, that forms a group. And this group has another name. We write GL2R for this group. This GL stands for general linear group. General linear. This 2 is 2x2 matrices. And invertible. And it's assumed invertible, and this R is saying what kind of entries. All right? So this is a group, right? And your linear algebra classes, like secretly, the whole semester, all that SA, S inverse, diagonalizability, Jordan form, all of that, it was just one in-depth study of this group with different ends. All right, I'll do another one. Another example. The group is the set of 2x2 matrices with real entries. All of them. And the group law, the group multiplication, is the addition of two matrices. Does GLN group always have matrix as its element? Yes, n by n matrices. Specify the types of entries, like real numbers. Yeah, that's what GLN means. It's just we just gave symbols for it. Okay, addition of matrices like this. I'm just doing 2x2. You can do 3x3. I just need to for concreteness. What do we mean? We write the symbol plus this time for this other operation, not multiply. We don't want to write multiply because it's going to get confusing. Since there's like a similar sister situation involving matrices where the multiplication symbol was already taken up. So we're going to use plus as our symbol denoting our binary operation. And what I'm telling you here, I'm telling you what the binary operation means. So this equal sign is actually a definition. Some equal signs are definition equal signs because someone is declaring that this is what plus means. And other equal signs are equal because of the laws of the properties. It's just 5 equals 5, that kind of equal sign. Okay. So this is A plus A prime, and B plus B prime, C plus C prime, and D plus D prime. There, that's what we mean. It's component-wise addition. Okay, associativity, because adding numbers was associative, and all you're doing is adding numbers in 4 different slots. So, because adding numbers was associative. Okay. Is there an identity? Yes, the identity element, or the one that serves as identity, is the 0 matrix. Inverses. Notice the confusion of the language? You got to get used to that. I'm purposefully writing inverse because that's what was written in this, just, you know, learning math means memorizing the book. And look, the book said inverses right here. So inverses. Inverse of an element. The inverse, or something that's, if you have an element A, B, C, D, the inverse and inverse for this is negative. There. Inverse is negation. Again. Yeah, this is obvious. All right. So there. Okay, so now you start to see that when someone says a group, you got to sort of just double check with them. You know, what is that operation that they're thinking of? What is the algebraic operation of combining 2 elements to form a third that they're studying, or that they're concentrating on, or that they're asking a question about? Sometimes there might be opportunities for confusion, like, oh, what do you mean? Are you talking about addition or matrix multiplication? It's usually clear by context that they could only be talking about one or the other, but just remember to specify explicitly what the group operation is. Okay, another kind of example. Another example. All right. So actually, before I do the other example from modular arithmetic, I'm going to talk about this one more time. Okay, now suppose someone said, look, I'm going to take this 2x2 matrix with addition group. I'm going to remove the group law and just think about that set 2x2 matrices. But maybe they decided, you know what? I'm going to come up with a new example. Group law is matrix multiplication. After all, nobody said that you can't multiply non-invertible matrices. You can multiply any two matrices that have the same shape, square matrices. You can do that. You just do the same formula. Okay, so there's a binary operation on the set of all 2x2 matrices, and someone just wrote, oh, consider that group. Yeah, that's wrong. That's a non-example. That's not an example. Because not everything in this set has an identity element. Because not every matrix has a multiplicative inverse, has an inverse with respect to this group law. I'll give you a very stupid example. Like, for example, 0, 0, 0, 0, e.g. What the hell other matrix are you going to multiply this one with to get the identity matrix? The identity matrix has to be the identity element in this. If this is going to be a group, the only option for the identity matrix, for the identity element, is 1, 0, 0, 1. So what are you going to multiply this matrix with to get 1, 0, 0, 1? Nothing. There's nothing out there. But there are other examples too, like just even this example, like any matrix that has rank less than 2. There's no hope of inverting it. Okay? So there you go. You got some non-example. Though it's a perfectly good operation on 2x2 matrices. It's just not a group. And we're talking about groups because we're limiting our investigation to a particularly rich topic. That having inverses, identity, and associativity, it'll just combine to a glorious little subject. And if you don't have inverses, the subject becomes less glorious. So yeah, we're not going to be talking about that situation. Okay. So now I'm going to go on Discord. Go to the general voice chat. I'm going to ask you a question, and let's see if we understand something from this lecture. So students, populate the voice channel general, and we're going to go and think about the following question. Intrusive probe time. Okay? Time for your intrusive daily probe. All right, so let's see. I'm going to go into general, and everyone's here. No one wants to actually talk. That sucks. Put some background music as my students get in order. Oh yeah, two of you want to talk. Okay, good. Okay, so here's a question. Here's a question. Is the real numbers, this is the set, and this is the binary operation. Usual multiplication of numbers, is that a group? Okay, we've got some people. How about someone, one of you in the voice chat, why don't you tell us what's going on so that it stays in the video, My videos get uploaded to my YouTube channel. I have a YouTube channel now. So I want to hear why people think it's not a group, etc. Or if they think it's a group, tell me why. Either I to Suk or another student, go ahead and tell me what you're thinking. What's going on with this? Okay, there you go. Yeah, another student? I can't hear you. Maybe I've got an issue with my Discord. I have a problem with my Discord? Hold on, this is good to know. Let's try to settle this. Let me see if I have an issue with my Discord. Output. All right, can you talk? Another student? Can you say something?
Hello?
Yeah, I hear you.
There we go.
Okay, great. Great.
I say it's not a group.
Okay, and what's going on?
Like in the last non-example, 0.
Yes. What's specifically wrong with 0?
You cannot multiply it by anything to make it the identity.
Exactly.
Which would be 1.
The problem is that not every element has an inverse. And there's exactly one issue, 0, specifically, right? Good. And so now what I'm going to do is I'm going to ask you, whoever that was another student. I'm going to ask you, can you fix it? Fix it.
Do the real numbers without 0.
Yes, exactly. So real numbers, non-zero real numbers. Numbers under multiplication, right? And where multiplication is assumed, the reader knows what we mean. Multiplication of numbers, just the old kindergarten. Okay? And we have a symbol for this non-zero real numbers. You take the thing that you were talking about, and then you put a little X on top of it. Because you like X'd out the 0, you just like X'd it. Okay? That's why. All right, so you just put that. That's how we write it. With so this thing forms a group. Good, we fixed it. All right. Now, actually, there's something funny about this. This R cross, the set of non-zero numbers, it kind of has 2 parts. There's like negative numbers, and then there's positive numbers. And if you look at the like positive real numbers with multiplication, this also forms a group. Because like, you take a positive number and do 1 over it, that's the inverse. Then it'll still be positive and non-zero. So this thing is also a group under multiplication, with 1, the number 1 being the identity element. Absolutely. Yes, Sloth. So now Sloth is starting to believe. Exactly. You just got to be careful out there. Awesome. Okay, here's a puzzle that I want to leave for any. Are there any students here that don't have to immediately leave and are willing to talk about this example? It'll stay on the video, on the VOD. So people who do have to leave can still watch what I'm about to say. But are another student or Itasuk or AI or whatever, are you guys willing to talk about this question?
Yeah, sure.
Yep. Okay. You don't have to run somewhere real fast. Okay, that's good. So those who have to run, you can leave. You can watch this discussion later. Okay, here's a puzzle. One of you people in Discord, we're still lingering here. Okay, can you find a group which has exactly 59 elements? That's a fun puzzle. Is there one?
Are the integers mod 59 under addition a group?
They absolutely are, and that's a great example. So AI gives us an example. So it's another important list of examples that I didn't get to in the 45-minute lecture, but of course I'll talk about on Monday more. So his group was the integers mod 59 under the operation of what? What was it?
I had said addition.
Addition. It's very important that you say addition. Otherwise, it's wrong. So, under the operation of plus, but plus meaning modular arithmetic plus mod 59. Okay, this is actually a group, and it has exactly 59 elements because the elements are 0, 1. Notice how I write these little brackets because, well, now we're talking about equivalence, the equivalence classes of integers under the equivalence class called congruence mod 59. So there are exactly 59 of them, and they have these names. There are exactly 59 elements. And how do you add two elements? You do modular arithmetic in the brackets. So like 2 plus 58 is 1. Well, it's 60, but 60 brackets is the same equivalence class as 1. Okay, so 2 plus 58 is 1. All right, and this notion of adding, this funny adding operation of remainders, or however you like to think about modular arithmetic, add and then you're on a clock, so like all that matters is how far you went from 12 o'clock or whatever you think of with modular arithmetic. 2 plus 58 is 1 in this group. Okay, and this addition operation is associative. You can check that. 0 is the identity, or is identity element. It serves as identity. And negation, again, but the opposite, the inverse of 3 is 59 minus 3, if you'd like to think of it that way. So 59 minus 3 is 56. All right? This is inverse to that. You add them both. Oh, this is commutative too. It's a commutative group. All right? So yes, there is a group which has exactly 59 elements. And the notation for this group we denote by Z, quotient, collapse via an equivalence relation. Z mod n times Z. So n is 59. Z mod 59Z. And then that's the set. And the operation is plus for modular arithmetic. So this is the name of a group that has 59 elements. And 59 was not special. These examples are absolutely essential to understand and have as a toolkit, because these are the examples of finite cyclic groups, just more zoology. Okay, so Z mod NZ under addition forms a little group. And so every number, we just established that you can have groups of all sizes. Every size, every finite size you can imagine, there's a group out there. that has that many elements. One curiosity you might have is like, are there any other examples of a group that has 59 elements? And we'll have to talk about that question, because as it stands, the question has a little bit of vagueness in it. So that's what we'll do. This is what I was gonna ask you next. So just think about this question. Can you find a group structure? Group structure. That's another term. Group structure, a group law, a composition rule, a multiplication rule. Can you find one where the set is the unit circle? That's the set that we're talking about. And then can you figure out, given two elements in the unit circle, how to specify a third element so that the unit circle becomes a group? That's just a little puzzle for you. And on Monday, I'll maybe tell you the answer to that puzzle. Okay, so that's the end of the material I wanted to sort of cover today. The first introduction to the concept of a group. Next class, we'll prove our first little baby theorems about what's true in a group. Why is there only one identity element? Why are inverses unique per element? And then we'll proceed from there with more and more examples tossed in. And we'll be using our third eye technology, which you probably don't know what that means unless you've seen some of my other classes. But we will be using the third eye technology to investigate some particularly beautiful examples of groups. Okay, so that'll come on Monday, Monday's class. All right. So with that, the class is over. But I do know that there was a student who wanted to discuss a problem from the homework. His name is Mo. I'm just gonna say Mo. And so Mo, are you still around? And did you still want to talk about that problem? I don't know if Mo is even around. Oh, that's a great... Okay, so Mod's not here anymore, so I'm not going to talk about that problem. But because the problem is just... No, it's a different Mo. Biomed Mo is not taking my class, unfortunately, on Pucci. All of my streams will become available... Yeah, from now on, they'll be available on YouTube. I still have to... I don't know. It's a pain to upload previous things. So from now on, they'll be available. But just mostly for my students so that they can have a place to go watch it 5 weeks from now after Twitch takes it down. Okay, so Ryan Looney had an interesting comment when discussing this example of 59 elements. They noticed that 59 is a prime. Now, in fact, Z mod 60Z, with plus being the operation, is still a group. And what's happening is Ryan Looney has gone a little bit ahead and has asked the question of, well, in modular arithmetic, you also had multiplication. Like bracket 3 times bracket 5, you do 3 times 5 and collect remainder and put a bracket. Yeah, that operation has the same kind of problem as this example had, where the 0 element will never have an inverse. And so you might think, oh, let's just remove the 0 element and try to form a group out of that situation. And Ryan Looney knows of a fact much later on that this is only going to work when the number is a prime. And that's something I'll talk about soon, probably maybe on Monday if we have time for more in-depth examples, but definitely by the end of the week on Friday, we will have that little prime discussion about trying to make multiplication, modular arithmetic multiplication. When is that a group law? On what collection of remainders, mod n? And what kinds of n's? So that's what Ryan Looney was actually thinking about. Yeah, it was a trap. Okay, no, that okay. Whatever. All right. Okay, so there's a bunch of trolls. Okay, Guru is just having a great time in chat as usual. Okay. All right, good. It's a good crowd we've got here. 14 people and 5 people in the class. So a bunch of perverts looking in. Awesome. Okay. So you guys know that right after, like, in 1 hour, I have to, like, make up a Calc 2 lecture. I don't, before COVID, things like Calc 2, like, I just sort of walked in and started talking. So, like, but now I can't do that because then the stream will be a complete garbage pile of garbage. So I have to, like, think about examples beforehand, and I think 1 hour is probably enough time. So I should probably get out of here. I guess I have to, send you guys somewhere else. Go troll some other person. Let's see. Let's see. Let's see where I can send you folks. You guys want to make a lot of money? Hey, chat. Put 1 in the chat if you want to make a lot of money. Oh, Gath is streaming? Okay. 1 if you want to make a lot of money. 2 if you want to learn organic chemistry. There's only like 10 of you. Not 14. 2 organic. Oh my god, organic chemistry is totally winning. Wait. Do we have a majority yet? Money is overrated? I don't think so, actually. Probably one of the biggest problems that people face. Like, probably one of the biggest stressors of, like, 99.9% of humanity all time. But I'm glad it's overrated for you. Happy for you. Okay, so it's Gath. Gath it is. Let me get Gath in here. Let me get Gath going. Gath Wagel. Yeah, there you go. There you go. Here we go. Go learn some organic chemistry. Start that thing. Start that raid. Something went wrong. Something went wrong. Gath is unable to be raided? Oh, has she turned raiding off? All right, go learn how to make money, folks. Go learn how to just scam poor people. Ready? Go do that. And then teach me how to do it. Okay. Gath can't be raided, I think. All right, we're going to go to our good friend over at over on Wall Street. They're like they're in the New York Stock Exchange place. They stream straight from there in the middle. So go check them out. And say hi and be good. Be good. Be good, people. Is that working? Did I raid? Yes, they are insider traders. Yes, absolutely. They are in the U.S. Congress too. So there you go.